Hey everyone, it's Miss Crane again, and I'm going to do these videos, and I want to be upfront with you guys and say that if for some reason you like doing the reviews in person, when I used to do them on Mondays from 6 to 8, you liked that better, were able to ask me questions, then by all means you can talk to Dr. Yang or send me an email. I don't mind personal emails, even if it is constructive criticism. I'm completely fine with that. But if you really like these reviews, I know that Dr. Yang will be asking you in class if you like them better on YouTube or in person. So if for whatever reason you like them better in person, you can let me know. I liked this idea personally because I know it could reach out to more people that may not be able to come to these reviews. So that's why I really like them, and I decided to do it again. She left it up to me in order if I wanted to do it at night or this way again. So I chose this. So please give me feedback or her feedback, whoever you feel more comfortable with. I don't care if you tell me you hate them. It doesn't bother me at all. Whatever helps you more, that's what I want to hear. Okay? So, besides that, if you've ever watched any of my reviews before or come to my reviews, you know the two big things that I say for Dr. Yang's test is to review her PowerPoints and to review these workshops. So, that's what I'm going to suggest to you, and I always say at every review. So, look over her PowerPoints, 2 of them. They're not that many slides. There's only 2 chapters, right? So review that and review this workshop, and I'm going to be going through the workshop and give you little hints along the way, as always. Now the first little hint I'm going to give you before we actually start going through the workshop. She likes definitions for certain multiple choice questions, right? So if she's going to ask, one of the ones I know teachers love to ask is the difference between the Arrhenius theory and the Bronsted-Lowry theory. So what's the difference between Bronsted-Lowry acid, Bronsted-Lowry base, and the Arrhenius acid and base? You want to know the basic definition that Arrhenius acid means that it's an increase in concentration of hydrogen ions, and then if it's an Arrhenius base, it's an increase in concentration of the hydroxide ions. Whereas Bronsted-Lowry acid states that the acid is a proton donor, and the Bronsted-Lowry base is where it's a proton acceptor. There's always that one multiple choice question where they ask you what's the difference between the two. They basically mean the same thing, but their definition is slightly different, right? So, now let's go on to move on to our chapter 16. And I will write bigger. Sorry, that's a little small. And I know you guys can full screen this, so hopefully you can see everything just fine. And if you have any constructive criticism in general, if you like the videos but you'd like me to do something else, or this is normally how I run it, but if you have any suggestions for me, you just go ahead and let me know, and that's what I'll do. I'll try to incorporate that if I think it'll work. So anyway, moving on. So now for our very first question, if you want to, I always go through these workshops, so go ahead and pull them out. And you can pause the video right now and pull them out, okay? So now I'm just going to keep moving on because I want to get through the material, because we have an hour for each chapter. Right now I'm just doing this first hour, right? And then later I will do chapter 17, but I kind of like to split it up. I think it's easier for you guys to pay attention if things are split up. So, and it takes 30 minutes to upload just an hour video to YouTube. So this is what we're going to do. First question, if you have it in front of you. If not, I will, continuously tell you read out the question and write it out, but it's easier if you have it in front of you. Designate the Bronsted-Lowry acid and the Bronsted-Lowry base on the left side of each of the following equations, and also designate the conjugate acid and conjugate base of the right side. So here we are, NH4+. And on your tests, of course, you want to write aqueous or liquid or gas. But for simplicity and for time's sake, I'm not going to write that. So here the whole equation is given to you, right? Okay. So it says we want to designate which is the Bronsted-Lowry acid, Bronsted-Lowry base, conjugate acid, conjugate base. So which side do I label Bronsted-Lowry and which side do I label conjugate? These are always going to be labeled as the Bronsted-Lowry. So your reactants will be the Bronsted-Lowry. You will always write your conjugate acid or base for the products. So if you're confused, you start writing Bronsted-Lowry here. No. Always write Bronsted-Lowry for your reactants, conjugate acid or base for your products. That's always going to be the same thing every time. So, what are some easy tricks to find out which one's the acid? So, we know the acid is the proton donor. So, obviously, what is the only thing that has protons? What does proton mean? That H plus means proton. Okay? So, what is the only thing here, what is the only molecule here that could donate a proton? We know Bronsted-Lowry acid donates a proton. This is the only thing that can donate a proton. So, obviously, this is our Bronsted-Lowry. And you can label it like that, BL, Bronsted-Lowry acid. Therefore, this has to be our base, right? So, this is our Bronsted-Lowry base. Make sense? It should. It's pretty easy. Now another trick, if you're confused on if you see hydrogens somewhere, right? Say both of these molecules had hydrogens. If you see that, the best way to figure out which one's the acid, if they are charged, so if they have an ion, the acid is always going to have a plus, and the base is always going to have a minus. Now, there are going to be instances like the next one where everything's neutral and there are no ions. But if there are ions, it should be very easy. You should either find out where something can donate a proton. So obviously this is the only two out of both of these molecules that can donate a proton because it only has, this one is the only molecule that has hydrogens. But say you have two charged molecules, you're completely confused. This plus will always mean that it's the acid, and this minus will always mean that it is the base. So say they're both charged. That's how you can figure it out as well. Like I said, not always going to be the case, and we'll see in the next one. So now, if I found out this is my acid, on the opposite side, so I know that this is going to lose, right? It's a proton donor, so that means I'm going to get rid of one H. So over here, it got rid of one H, right? It went from NH4 plus, got rid of one H, got rid of one of those pluses, H pluses, so it now becomes NH3. So, basically, this, I don't know if this is chemically correct to say, it's reciprocal on the other side. So from NH4 over to NH3, we always know if it started out as an acid, that will be the conjugate, and you can write it just like this, C-O-N-J, conjugate base. So if it was an acid on one side, it's become the conjugate base on the other. And that is basic. Ammonia is basic, and ammonium is acidic. So now we know bases accept, right? That's the definition. Bases accept that proton. So we see over here, it accepted an H. So that means it's now the conjugate acid. So the form over here is the acid. The form over here will always be the conjugate base. The form on this side, the molecule on this side, we figured out to be the base. So the molecule on that side will be the conjugate acid. So hopefully that makes a little bit more sense. You can actually pick out exactly what little tricks that can help you figure out which is which. But again, it's not that difficult. Now number 2, we have all neutral molecules on the reactant side. So this one might not be as obvious to you. So now look, now what do we call H2O? Remember that that term, amphiprotic, means that it can act as a Bronsted-Lowry acid or base, right? So since we can't figure out what H2O is, we have to look over here. Now, it may be confusing because you see this H. Well, maybe this is an acid because I have H's. No, see, when it's connected to like a hydrocarbon like this, those H's are non-acidic. So they're connected to this C, so that means they're non-acidic. So that is actually not like this molecule actually looks like. So that is actually not an acid. This will act as the base. And how would I know that? The only reason I know that is because if I look on the other side, it added a hydrogen to it, right? So if I add this accepted, right here, accepted a proton. Proton acceptors are bases. So that's a Bronsted-Lowry base. Therefore, the other one has to be the Bronsted-Lowry acid by default, right? Because we don't know what H2O is by just looking at that. So now we have, sorry if you hear my dog in the background barking. She likes to bark at people that come by. Here we saw proton acceptor. So now, since that added an H, it becomes more acidic, right? So that means it's my conjugate acid. And here, obviously, we always know OHs, we see OHs as basic, right? So that would be my conjugate base. So that should be fairly easy to figure out, right? Now that we have a couple little tricks about the ions, what accepts, what donates. If you're given the full equation, it should be pretty easy which one is the Bronsted-Lowry base and which is the Bronsted-Lowry acid, okay? So now let's move down to number 2. Predict, yeah, we should be able to fit it on here. Predict the products of the following acid-base reactions and predict whether the equilibrium lies to the left or lies to the right of the equation. So we're looking at these equations and we actually have to write the products for these. And the first one, we did not have to write any products. Right? So again, and we have to figure out now if the equation lies to the right or if it lies to the left. So I will give you a little trick on how to figure that out as well if you're confused about it. So another hint for you guys. Anytime I see that COOH, it's normally, for all intents and purposes for this test, that will be a weak acid. So, I mean, I instantly look at that COOH and think acid, right? I do because I've seen it 1,000 times. But another way, even if you don't remember that little hint right there about that particular part of a molecule, it can have any type of chain, right, on this end side. It can have a bunch of carbons and hydrogens. It'll still mean that that's a fairly weak acid because that is the acidic hydrogen right there. Anyway, now if I look at this minus, what did I say about it up here? That it was going to be the base. It's exactly what it is here. I have that minus, it's going to be the base. This I knew was an acid, so it's fairly easy for me to understand, but that should have been obvious from what I taught you in number 1, okay? So, let's go ahead and say Bronsted-Lowry acid, Bronsted-Lowry base. And again, because it has that minus, it's going to want to accept that plus, that H plus, that proton, right? So perfect. Now we at least labeled that, and we can create the other side of the equation. And I'll write it down here so it's not crammed over there. If that's the acid, what's it going to do? This is the acid. Proton donor. I told you, this is the acidic proton. Anything that's like the hydrocarbon, carbons and hydrogens together, will not be the acidic. That's why when we're looking up here, these are just carbons and hydrogens together. They are not acidic protons. These, connected to that oxygen, are. So what we do is we say, if it's a donor, we take that H away. And this is an H plus. So that makes this molecule right here, taking away an H, a minus. So we have CH3, COO minus. And again, these will all be, they will all be aqueous when you make these, right? Except for water. Water will always be the liquid. But otherwise, when you're writing the conjugate acids and bases, they should all be aqueous. So now, I write, this was given to me, so I didn't write it out. But now, since this is an answer that I need to write out, I'm going to write aqueous for you, so you guys remember to do that, right? Now, what is this going to be? If that's the base, it's going to accept. So I'm going to say it's H2S or HSH. I don't know if she would take off if you put HSH, but you can put the H's together, right? H2S, aqueous, which makes this, so this is the conjugate, came from here, so it's a conjugate base. It came from here, so it's going to be the exact opposite, conjugate acid. Now, how do I figure out, I actually asked Dr. Yang a question today for you guys. How do I figure out which way it lies? If it lies towards the reactants or if it lies towards the products. Or you can say products or reactants, or you can say lies to the left or lies to the right. The actual question says lies to the left or the right, which is fairly self-explanatory too, right? So I asked her today, now, are they expected to know certain trends, or are they going to give a chart? She said you will be given the chart on the test. So that means you will be given this chart. Sorry, that's my dog again. Anyway, you will be given this chart on the test. I hope that you can see this all right. Now, for our question, we are looking for, now, what do I compare? So let's look first down here. What should I compare? You're always going to want to compare acid to acid or base to base. And try to find the ones that are on the chart, right? If you can't find it on the chart, try to use the other one. So let's just say, let's just look at acid versus acid. So acid on one side versus acid on the other side. So that's what you're going to compare to figure out if it lies to the left or the right. Okay? So I'm going to be looking at bronzed lauric acid and the conjugate acid. And I'm going to compare the two in order of strength. So if we look on this chart, hopefully it, yep, self-evaluates here. If we look on this chart, we can see there's H2S, and here is the CH3COOH, acetic acid, right? So this one is stronger on this relative acid strength increasing. So this is stronger than this. Does that make sense? Because up here is the strongest, here is the least strong, right? So since this is stronger, this is how the trend goes. This is stronger, which means I'm going to have my products more into completion. So if your reactants are stronger, your equilibrium lies towards the products or to the right. If my products are stronger, then my equilibrium will be forced over to the left or the reactants. If you write reactants, products, or left or right, whichever one you prefer, it's fine. You'll get the right answer on the test. So that means this equilibrium lies to the right. And you can use that chart, which is excellent. Some people may have known that those two, that this was a stronger one, but you're not expected to know that. So you will be given the chart and you have to evaluate their relative acidities. And again, you probably could have used the bases. Yeah, you could have used the bases just fine. They're both on there as well. So you could have just evaluated this base versus this base, and it would have given you the same answer. Okay? So hopefully that makes a little bit more sense on how to figure those out. It's pretty simple. I'm not going to go through B. If you have questions on it, please ask your TA. And then again, if you're really desperate to ask me a question because you like the way I teach or whatever, feel free. Feel free to send me an email as well. But I'm trying to do these so I can get more people, which I think makes sense, in my mind at least, to get more people to be able to view these videos. Okay? So, hopefully those make sense. And we'll move on to the next. So now we have, at the bottom of here. Now here's a couple of little tricks that I think a lot of TAs don't actually go over. For the next part, number 3, so look at your number 3. Calculate the concentration of OH and pH for 2 different problems. So we are calculating the concentration of OH and pH. Again, if you have just tuned into my videos, I try to teach to the person that knows the least. So I go very slow through certain things. But in case you forgot, OH minus means the concentration of the base. So this is base. Concentration of the base. And what do I mean? Anytime anything is in brackets, that means it means molarity. What does molarity mean? Mole per liter. Okay. I try to teach so that even if you are clueless from the previous chapters, you could probably catch on. At least that's my goal. So now, calculate both of these things. Concentration of base. Now, some people may be confused. I just had a question on this, so I'm going to mention it real fast. That means you are they mean the exact same thing, but teachers like to interchange them. They'll interchange H3O plus and H plus very often, and they expect you to know that they mean the exact same thing. So if you see this in parentheses or you see this in parentheses, just think H and a plus, they mean the exact same thing. People get very confused by it, but you are finding the concentration of the acid. Okay? So that's what it means. They shorthand it sometimes to just the H plus, right? But it means the exact same thing. You're finding the concentration of the acid. Okay? Next. So now this problem says, I'll write out its dimension or its parameters. 1 milliliter of a 1.75 molar NaOH. This is all given. It's diluted to 2 liters. So it says calculate this and pH. So both of these things, right? Now, this is fairly simple. Any time, so it's NaOH, any time you have a strong acid or strong base, it should be a straightforward calculation. What do I mean by that? Weak acids and weak bases will have that ice chart. Why is that? Strong acids and strong bases completely dissociate. So they will go to completion. Whereas weak acids and weak bases are, they're in some sort of equilibrium between products and reactants. These go to completion, straightforward. Weak acids and weak bases, you see typically you have this. Between weak acids and weak bases, you have A plus B, and then C plus D. D. I meant to write that as a D, sorry guys. Anyway, what I'm trying to show you here is that weak acids and weak bases lie somewhere in between, whereas strong acids go straight to completion. So you don't have to do ice charts for the strong acids. Right? So if it's just a straight, now there are, you'll get into more complicated ones and ice charts, and we'll get to those, like titration type ones where you're adding base. So we'll get into those though. For right now, this is a straightforward. They're asking for OH, the concentration of OH, the base, OH minus, and the pH. So this should be straightforward because it is a strong base. Now, in this question, it says that we have this and it's diluted to 2 liters. So it should be a straight up M1, V1, M2, V2. We plug in our molarity, our first two, and then we plug in the volume to find our so we're trying to find concentration, right? So this should be pretty easy. I'm trying to find concentration of OH. So I have here, and then I want to remember, every time your units should match. So we want to get milliliters into liters. So we have all of our units canceling out like they should. Now, of course, I ran out of room because I'm trying to write big for you guys so you can see it. But it's M2 times just that 2 liter, right? I find my M, my second concentration, which is what I'm looking for first, right? I'm finding a concentration, is 8.75 times 10 to the negative 5 molar NaOH. Right? So that was just literally plug into my calculator and divide by that 2 liters, as long as all my units are the same. So now that I have that, I know, since this is a 1-to-1 ratio, Na, so if I split this into its ions, Na plus OH minus. There's not 2 OHs, there's not 2 NAs, there's just one each, right? There's one Na and there's one OH. That means that this concentration goes for each of them. It's 8.75 times 10 to the negative 5 molar of my sodium ions, and it's 8.75 times 10 to the negative 5th of my OH ions. Hopefully that makes sense. Because if there were 2, say that NaOH, say we had actually calcium hydroxide, which that is its formula. If we had the same molarity here, that means my OH ions are 2 times that value, and that's going to be the concentration of OH for CaOH, because there's 2 hydroxide ions for every 1 calcium ion. But since we're looking at NaOH, this was just a side example here, guys, and there's only 1 sodium to every 1 hydroxide. So it's just 8.75 times 10 to the negative 5 molar of sodium ions, and that same value for OH ions. So I know I repeat myself a lot, but that's just for you guys to understand the concept better, okay? So now I found my concentration, right? My concentration of OH, I'm looking for OH, right? So my concentration of OH minus is just this 8.75 times 10 to the negative 5th. Because there's only 1 OH here. Otherwise, I'd multiply it by 2 if there are 2, multiply by 3 if there were 3 of them. Okay? So that's pretty easy. Now, I'm looking for pH. What do I do to find pH? Well, you guys probably know to use the negative log to put that P in front, right? So putting a P in front of pH or putting a P in front of H or putting a P in front of OH, meaning negative log of that concentration, will give me that P in front. So, but here I found OH ions. I did not find H+. This means H+ ions, the P of H+. But I have OH ions. That means if I do negative log, it's POH. I'm looking at the base, so it's POH equals negative log of that 8.75 times 10 to the negative 5. Make sense? You found the OH, you throw that number in here, that's the concentration of OH, meaning POH. Hopefully that makes sense, okay? Now, if I want to find pH, what's the simple equation? pH plus POH is equal to 14. So if you're given one, you can find the other. Just a lot of people will stop at this part right here, and you'll get a lot of credit for that, but you need to remember that equation. If you have OH concentration, then you're finding POH. If you have H plus or H3O plus, anything with a plus right here, H plus or H3O plus, then you will be finding pH if you do negative log, and then you don't have to go any further. I hope that makes sense. So pH plus POH, 14. That means if my POH, so this number right here, ends up being 4.0058. So if I plug that, pH, sorry I knocked the computer, pH plus 4.058 equals 14. That means I literally just take 14 minus that 4 number. So it should be 9. Yeah, your answer is 9.942. And all the keys are posted online, so you should have all the answers to everything now, okay? So again, my answer is 9.942 for pH. Because I'm given a concentration of OH, but I want the P of H+. Okay? Alrighty, guys. Moving on. And we're 30 minutes in. These take so long, all of these. So I'm just going to do, some of them I'm just going to do like one example instead of doing both of them, right? Okay, so the next one. The next question is a solution formed by adding 5 milliliters of KOH to. So for this problem, again, it's asking the same thing. It's asking for the concentration of OH minus and the pH, just like the previous one, because this is part B, right? Part B of number 3. All right? So we have a solution of them added together. So we have 5 milliliters. I'll write that up here. This one's pretty simple. I'll go through it quickly because I definitely want to get to those ice charts. Everyone hates those, I know. But I think after you get done with me tonight, you will understand them like no other. So we have this, and we're mixing 15 milliliter of 9.5 times 10 to the negative 2 molar calcium hydroxide. Right? So I'm mixing these two together. I need the concentration and then its pH. Very similar to what we did last time. But what we're going to do is we're going to find moles. What can I do to find moles of each of these? What I'm going to do, multiply them together. What does this mean? Mole per liter. That molarity, always remember, molarity equals moles per liter. So I can literally multiply by 0.0. Make sure you get everything in the right units, right? That's why they harass you at the beginning of Chem130 to make sure you're getting everything in the right units, is because you use a lot for 130. Get rid of that. I have my mole value. Everyone should know how to do that. Even if you have no idea what's going on in 130, you should know how to do that. Now, that's how many moles I have. Okay, that's how many moles I have just multiplying these numbers together. I want moles of OH, right? So, how many potassium ions are here? 1 to every 1 OH. So it's 1-to-1 ratio. That means that this is my answer for OH ions for this first part. Now for the next part, if I quickly write that out, the same type of thing. Mole per liter times 0.015 liters. I have to do one extra step here, because here I'm getting moles, right? I'm getting just moles by itself, but there are 2 to every 1. Remember, I used this example in the last problem as an example. There are 2 hydroxide ions to every 1 calcium. So I have to say 2 mole OH to every 1 mole calcium 2+. So I have to multiply whatever my mole value is by 2. So I hope that makes sense to you guys. If you're trying to find concentrations, or moles, in this case is moles first and then concentration, you need to make sure you account for how many are there. So if you see 3, then you would have to multiply this by 3, right? Okay. So that means my answer here is 2.85 times 10 to the negative 3 mole OH for the second part. So this was 1, 2, 1, 2. So hopefully that's labeled a little bit better for you to follow. Okay, now, how do I find my OH concentration? Really, really easy. I add both of my moles together and then divide by the total amount of liters in the problem. So I say this, 5.25 times 10 to the negative 4 mole OH plus this 2.85 times 10 to the negative 3 mole of OH. I can't write it. Now, what are the total number of liters? The total volume, because remember, we're looking for a concentration, so it's mole per liter. What's the total number of liters that is in this solution? It's 5 plus 15, right? So we have 20. And we want it in liters, right? So it's that 0.005 liter plus that 0.015 liter. That's going to be my concentration. And that's what we want right here. So my OH minus is all of this added together and then divided by the addition of both the volumes. So that ends up being a concentration of 0.16875. You could have just left it in 3 significant figures, I think. Yeah, you could have just left it in 3 and been fine. Mole OH. Now, and then remember what I told you when you're doing pH. Same thing as the last problem, so we're not going to go through it. Because then we'll have a solid, like, 23 minutes to do our fun ice charts, okay? So hopefully that makes sense. Pause the screen, rewind, rewatch, whatever you need to do in order to understand this concept better, okay? So now we're going to move on to our lovely ice charts. And why is it an ice chart? What did I tell you about ice charts just not too long ago, right before we did this problem right here? I told you that you will be using them for a week. So be familiar with what a weak acid looks like. Yang's not too tricky about weak, like putting like strange weak acids on there. She's going to put fairly common ones that you should know. Remember, one of the ones I told you should know, I told you that should be a big sign that it's a weak acid. You don't even have to remember that it's a weak acid because you have that little chart that she gives you. She lets you know. You're going to have this chart on the test. So if you can't figure it out, you forgot, take a look at this chart. Okay? It's a weak acid. It's a very common one. Maybe by me saying it 1,000 times, you'll actually remember without having to look at the chart. But anyway, let's move on. So this is number 4. Oops. Okay, this is number 4. Okay, so I will write out what's given. A solution of chloroacetic acid. And she gives this to you in parentheses, so this is all given. This isn't something you had to know off the top of your head, right? Again, ding, 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 weak. Need to use an ice chart, okay? Again, because it's only partially ionized, it lies somewhere, its equilibrium lies somewhere in between those reactants and products, okay? So, in this problem, it says it's 11% ionized. Oh, ionized. Okay? Using this information, calculate the concentration of everything. So you want to find the equilibrium concentrations. This is a big indication too. You won't always get, you know, how its percentage of ionization, but that's a big sign that it was only partially ionized, right? Which means it should be weak. So that's a big hint right there. But this is one of the easier ones, so there are a lot more hints. So we're trying to find concentrations of all of our products, and we're trying to find the Ka for chloroacetic acid. So, the first thing that we should do when we see something is percent ionized is find a concentration from that. That concentration from this percent ionized gives me the change in ice. So I see percent ionized, the first thing I'm going to think is that it gives me the C, the change in ice, okay? But how do I find out the concentration from 11% ionized? Change the percent into a decimal, so divide by 100, and then I multiply by this concentration, and that's my change. Let me show you. Concentration given times percent ionized as a decimal. Hopefully that makes sense. That is going to be my change concentration. So this is my initial concentration, which is fine, but then my change is going to be, so this is my change. Now let's actually set up the ice chart. What do I do to find my equation for my ice chart? I throw it in water, right? So if I throw this in water, in my ice chart we never include water. Why? Because in our equilibrium expressions, the Ka or Kb expressions, we only include aqueous, right? Our gases, right? But we're not going to run into that in this test. We're going to only include aqueous, okay? So water is never included in my Ka expression. It's never included in my ice chart, okay? So, but regardless, we'll write H2O for, so you know that's what I'm throwing it in. Now, remember, I said it was a weak acid. I can figure that out from the chart that she allows me to have on that test, okay? So if that's an acid, what does it do? Donates. We donate. So it's somewhere in between, right, that equilibrium, because it's a weak acid. So now I get rid of that H, right? It donates that H over here. So I get on my other side Cl, CH2, COO minus plus H3O plus, right? Running out of room, of course. So hopefully you can see that that's an H3O plus. Now, let's do our ice chart. Now, I'm writing H2O in there the very first time, so you know I don't include it. The next times, I will not write it in there. Ooh, let me write that. Now, again, if you hadn't watched my other videos, these are, obviously, both of these are my reactants. Those are my products. Reactants. Now, maybe sometimes it doesn't give me the initial. A lot of times it does, though. This is my initial, right? I am telling you in a bottle that this is my initial concentration. Water never included. So I'm crossing it out, showing you that it's actually there because that's how we get our products, but we never include it in this expression. I told you, this is my change. Now, initially, this is initial change equilibrium, right? Initially, that's what I'm given. I haven't mixed these two together yet, have I? If I have not mixed those two together yet, there are no products. This H3O plus is the same thing as H plus. You could have written an H plus there. Whatever you, I mean, if you actually do the equation, right, you donate this H to here, so it's H3O plus on this side. But you could just simply write it as H plus if you wanted to. You will not get points off. It's the same exact thing. So anyway, now, start out with 0 initially. This is what, on the product side, reactant starts out for what it gave me in the problem. Now, I told you my change is when they gave me that percent ionized. So, change. My reactants always do what with the change? Reactants always subtract the change. products always add the change. Same thing here. Okay, now my equilibrium is the addition of both of them. So if I say this plus, we add all of these together. Now this plus a negative is just going to be this minus, right? So 0.1 subtracted by 0.011 gives me 0.089. Type everything into your calculator, give it a whirl, because you know, sometimes people just type things in so fast they miss stuff. Okay? So both of these have the same values. If you can't see over here, this is H3O plus, this is H plus, and they both have the exact same values. So now, hopefully you got that, because I need to go on a different sheet of paper. Now we need to write our equilibrium expression. So you should have done this on the last test in order to figure out Ka. So in this problem, it asks me for my equilibrium concentration of everything. My equilibrium concentration for this molecule, chloroacetic acid, is this. So you would say bracket this molecule and bracket equals that. Bracket this molecule and bracket equals that concentration. Bracket H plus and bracket equals that concentration. So those are your answers for all the different concentrations. It asks for a concentration, it's asking for the equilibrium values. Okay? That's why you do the chart, to get down to the bottom. Now, it also asks for our Ka. And what does Ka equal? Only all aqueous products over all aqueous reactants. So my expression is the products and I'm going to drill it into your head. You could have written this as H plus and no one would have cared. So either or, fine. But it's this times this all over my reactant, which was what was given originally. So then I found all my concentrations, so I literally plug them all in. And your Ka value should be unitless, so you don't have to have any units there, okay? That's just Ka is equal to that. Okay, so my equilibrium constant is equal to that. This is my equilibrium expression for an acid. Ka means equilibrium for acid. Kb, equilibrium for base. Kw, equilibrium water. So that should all make a lot of sense, hopefully. Okay. So for the next one, this is more of a typical ice chart, number 5, and then we'll do a number 6, and we'll do part A on number 7, and then I think you guys should be able to. Yes, I think okay. Yeah, the next few ones after this one should be fairly quick to talk about. So we should have plenty of time. These ice charts take a lot of explaining. So we're going to move on to the next one, number 5. Yes. So calculate the pH of the following solution. We have propionic acid, which is given to us. It says acid, and it also has C2H6. I told you, Yang is not that tricky when it comes to weak again, I see that COOH and I'm thinking weak, right? And it says propionic acid, so we know it's an acid, but it's weak acid because it has that COOH. And it also tells me my Ka is equal to... Now, we're just going to set these charts up a little bit faster than we did last time because we should start getting used to them. Now, C2H5COOH. Now, we throw this in water. Remember, the first thing we need to do is find that equation. This is an acid, so it needs to donate on the other side. You throw it in water and you split it up to where, you know, you donate a proton and then you accept another one. I'm not going to put it in water this time, so you guys should be able to know what happens, right? This gets donated. This gets donated, so it is and you throw it in water, right? So it's always water. If this gets donated, then it's C2H5COO minus. And then my other, and again, everything is aqueous except for water, and that's why I'm not including it. You can, every time, add water like I did on the previous problem. No problem there. No one has a problem with that. Ice charts can or cannot have H2O. Either way is completely fine, whichever makes you the most comfortable. Just when you're writing H2O, make sure you know that that cancels out completely. So you'll never have it in your Ka expression, and you'll never have it in an ice chart. It'll just, you can X it out like I did on the previous problem. So here we are, C2H5COO minus, and then again, since it was an acid, we produce this H3O plus. So that will be in what's in my ice chart. So I had to come up with that. On this actual problem, it was given to you. But there will be times you have to come up with it on your own. So just make sure you know how to do it. And we've done previous problems like that. So we don't have to worry too much about it. So it's giving me this initially. Am I given any other value here, like percent ionized? Am I giving any other value to give me a change value? No. Ka could be used in the equilibrium expression at the end, but it can't be used anywhere in here. So again, my products are going to be 0. I don't need, you know, I have not mixed this in water yet initially. That I stands for initial. Now change. Always going to have minus. We're getting rid of the reactants and we're forming products. So we're just going to leave them as X's because we have no idea what they are. Alright? So now, equilibrium. What's my equilibrium? Remember I said I add both initial and change together. That means my equilibrium values will be that 0.95 minus X. This will just be 0 plus X, so just plus X plus X. What's my equilibrium expression like? It's going to be the exact same thing as what we just did. Ka, this is an acid, so this is Ka. If this was a base, this would be Kb. Don't screw it up because, you know, you'll get points off for labeling them incorrectly. Maybe like 0.5, not much, but just pay attention, guys. I know it gets stressful on tests. So now we're always doing products over reactants. And I was given a Ka value, so I can set this whole thing equal to this 1.3 times 10 to the negative 5. Now, there's a little trick, and they didn't teach it until now because you probably on your last test had to do quadratic formula, right? How can I get rid of that X to make my life easier? Because if I just say X squared and then this X is gone, my life is much, much easier. But there's a little trick. You have to know when to get rid of that X. When to cancel it and make your life easier. How can I assume that I'm getting rid of that X? You can look at your Ka value, and if your Ka value is less than 1 times 10 to the negative 3, which it is. This is negative 5, this is negative 3, so that is bigger. If it is less than 1 times 10 to the negative 3, you can cancel that X every single time. If it's bigger, if it's 1 times 10 to the negative 3 or larger, then you can't cancel it and you have to do the quadratic. So that means we're going to assume that this equilibrium value is just 0.095. But anyway, now I can just solve by saying Ka squared equals x squared. Makes sense? My life's easier because that Ka value was small enough. Now I multiply by this. I multiply these two together, get x squared by itself, and then take a square root, right? Take the square root of both sides, and just get x by itself. So that means my x is equal to, let's see, where did they calculate it? Yes, 0.00111 molar of, H3O plus. Well, actually, when you find x, you first say that it's just 0.00111 molar is equal to x, right? And then you can say, okay, my concentration of this value, this molecule, the base, the conjugate base, is this 0.00111. The concentration is also of H3O plus, the same concentration. The concentration of the concentration of this propionic acid is the 0.095 minus x. So I hope that makes sense to you, right? So I literally plug in all of these x's right here. And that's how I get my concentrations. This question asks for pH. It says calculate the pH of the following. So what value am I going to use to find pH? H3O plus. If I'm going to find POH, I'm going to find the OH minus, right? So if I want pH, it's P of H plus, right? So I want to find either, remember, you could write this just as H plus as well. H3O plus or H plus means the exact same thing. So if I'm looking for pH, I need to find this concentration to plug into the negative log of that concentration. So to find pH, I literally just said negative log of the H3O plus, which will be negative log of that 0.00111 molar. And that's my answer for pH. So that'll be your pH of this propionic acid, okay? So now moving on. Hopefully those are starting to make more sense so you can get into more complicated versions. Now, number 6, predict whether aqueous solutions of the following compounds are acidic, basic, or neutral. Write the hydrolysis equation if it occurs. So here, let's go over. Now, hydrolysis equation is where you would throw certain of, hydrolysis means like throwing it in water, right? So let's do the first one. When we're running out of time, so I want to do at least one of the next few, okay? So, first thing I'm going to do is split it up into its ions. If I split it up into its ions, we know NH4 is a common polyatomic ion. Everything's aqueous, right? NH4 aqueous, I just don't have time. Or I don't have space is what I meant. Br minus. So, where's that little chart? So looking at this, let me see if these values are on your chart. They may or may not. Yeah, they are. So let's look at this chart. Like we don't know anything about NH4 or Br minus. Look at, there's NH4 on here, NH4 plus. It's a weak acid. but it is an acid nonetheless. So we know that this is acid. And if we look, oh, it's not on here. But we can actually use a similar acid. We can actually use HCl as an idea, because our next one is Br, right? And the conjugate base, like we could use HCl or HBr, because they're both halogens, right? They're both halogens. HCl, HBr are both strong acids. So by association, I could use this and see that as the base form, Cl- or Br- would be negligible, or in this case, neutral. So this is acidic, and this is neutral. So we are going to write our hydrolysis equation. We are going to use whatever we can find that is either basic or acidic. So in this case, we're going to use, since this is neutral, we're going to use NH4+, because it's acidic, and that's what we're going to throw in water. So NH4, because we're writing the hydrolysis equation. Oh, we have to figure out if it's acidic, basic, or neutral. So since we found out our products, one was acidic and one was neutral, the overall is acidic. So this is an acidic compound. And again, you can use that chart, not bad. So my hydrolysis equation is throwing it in water. And again, this will be aqueous, that'll be liquid. So if that's the acid, it's going to donate a proton, right? And then this is going to accept one. Aqueous, liquid, aqueous, aqueous. So hopefully that makes sense. We don't really have time to go over another one, but that's what you need to do. You need to look at the products, figure out what is it more of, you know, acid versus neutral, base versus neutral, because then it would be a base. And look over the answer keys, because they are online already, okay? I'm trying to see if there's any like trick ones to it. And if you have questions about some of the ones that may be like a trick one, then D is a neutral compound. But again, make sure you reference this, because this will be on the test. I asked her today on purpose because I didn't know if she was going to give it or not. Some teachers do, some teachers don't. So just remember to reference that. So number 7. The hydrogen oxalate ion is amphiprotic. And this is the last one we're going to be able to do today, so I'm sorry guys about that. If for some reason the next video I make runs short, which I doubt because these ice tables always take forever, but I can go back to it. But like I said, I highly doubt that. So make sure to ask SI leaders, you know, tomorrow, or Danielle on Wednesday. The hydrogen oxalate ion is amphiprotic. Remember, amphiprotic means that it can either donate or accept that proton. Write a balanced chemical equation showing how it acts either as an acid towards water, or another equation showing how it acts towards a base in water. So let's write So for my first equation, I'm just going to pick. It says acid or base, right? So if it can act as both, it's amphiprotic, this ion is, then let's just say, I'm going to say this is an acid, and then this will be my base, because water is amphiprotic as well, so it can work like that. So if this is an acid, it donates that hydrogen, right? See? I got rid of another plus charge, which means this is going to be what? 2 minus. And then, if I'm getting rid of this one, it's gaining there. That's our common hydronium ion. And the reverse will be the case if I said base versus acid. right? So down here, if I change it, and it's a quick one to do, so I'll just write it out for you. Say I made this my base, and I said this is my acid. If this is the acid, donate, which means if I'm donating here, OH minus plus, sorry, this is up here too, OH minus plus, now I'm adding a hydrogen here, right? Because this accepts. If it's a base, then it accepts. So that means it'll be H2C2O4. And if I'm adding an H plus, what is that going to do? Remember to always keep those charges in mind. It's going to make it a neutral molecule, right? So those are the two equations right there. So for the next problems, let me take a look real fast. B is kind of a self-explanatory one, so if you don't understand it, have someone answer that question for you, a TA or anybody. If you guys saw my email, you can ask a bunch of different people. Let's look at number 8 real fast. Explain the following observations. So I'm just going to put this one up here since we're running out of time. Explain the following observations, and hopefully it stays within the screen. HCl is a stronger acid than H2S. That is because Cl, so for both A and B, you're just looking at, because even in B, there's 3 H's, 3 O's, 3 H's, 3 O's. Everything's the same except for phosphorus and arsenic, right? So AS versus P, and this is just a difference between Cl and S. You're just looking at which is, sorry, that was a screen. You're just looking at which one is more electronegative, right? So the more electronegative one will be the stronger acid. That's all there is for A and B. Now part C, if you have, the more oxygens you have, the more acidic it is. Okay? So that's all there is to that too. More oxygens, more acidic. More electronegative, more acidic. Okay? So those are the two trends. And then 9 is another ice chart. So if you don't understand that one, you should be able to follow it pretty well though. Okay? So hopefully this helped you guys, and I'm going to post it now.